This is Module 8, the network layer of the Cisco Academy's Introduction to Networks version 7.0 curriculum. The network layer is layer 3 of the OSI model, and this is where IP addressing is located. The network layer, it will provide services to allow end devices to exchange data. IP version 4 and IP version 6 are the principal network layer communications protocols. Previously, we had multiple other protocols, such as AppleTalk and IPX. Those, in most cases, are no longer used because it was taking too much of the administrator's work for a minimal amount of traffic. So most companies today have fixed on either IPv4 or IPv6. The network layer performs 4 basic operations: addressing the end devices, encapsulation into a packet. It takes a segment from layer 4 and encapsulates it into a packet to send to layer 2 to become a frame. It also controls routing and de-encapsulation, as when a packet enters a router, the router being at layer 3 and the frame coming in being at layer 2, the router will de-encapsulate the layer 2 information, basically stripping it off so it can examine either the IPv4 or the IPv6 addressing to determine which path to put the packet on to get to its end destination. The router would then re-encapsulate the packet to send it on to its next stop. IP encapsulates the transport layer segment. At the transport layer, the port numbers for the protocol that we are transporting are put on. That information comes down to the network layer. As seen in the diagram, the segment header from the transport layer, along with the data, is passed down to the network layer, and the network layer simply understands that as data. IP can use either IPv4 or IPv6 packet and not impact the layer 4 segment. The IP packet will be examined by all layer 3 devices as it traverses the network. As a packet traverses the network, the IP addresses will stay the same. Unlike the MAC addresses or the layer 2 addresses, as discussed in the previous chapter, will change for each individual hop the data will make going from its source to its destination. Because of the depletion of IPv4 addresses, one of the things that was developed to help alleviate the depletion was NAT, or Network Address Translation. We will not be discussing NAT here. It will be discussed in a later module. IP is connectionless in that when we send out information, we do not necessarily need to know if the receiver is there. It is a best effort system in that we try to get the information there, but if it doesn't arrive, there is not really a problem or a concerted effort to resend it. The user can request the information again or send the information again. IP is also totally independent of the media. Since the media is controlled more by the data link layer and how packets are encapsulated into a frame and placed on the media, the network layer does not need to know what type of media we are sending the data out on. So connectionless does not establish a connection with the destination before sending the packet. As in the example, this is like when we send a letter. We prepare the letter and drop it in a mailbox. We do not know if the receiver is there to receive the letter. So there is no control information needed, either synchronizations or acknowledgments. The destination will receive the packet when it arrives, but no pre-notifications are sent by IP. If there is a need for connection-oriented traffic, then another protocol will handle this. Typically, TCP at the transport layer will set up through a three-way handshake the connection so that we can be assured the connection is there, the receiving system is available, and ready to accept our data. As we can see in the diagram, the truck carrying the mail is nondescript. Same with IP in that the way that we carry the data, the network layer does not need to know. It could be either Ethernet, it could be fiber, it could be satellite, it could be wireless, or any other medium. Just like mailing a letter, the person mailing the letter does not need to know what type or brand of truck is being used to transport their letter from source to destination. IP is a best effort. It does not guarantee the delivery of the packet. Other protocols do that, such as TCP. IP has reduced overhead since there is no mechanism to resend data that is not received. That is another part of TCP at layer 4. IP does not expect acknowledgments. And again, TCP would handle that at layer 4. And IP does not know if the other device is operational or if it has received the packet. As in the case of TCP, that is set up beforehand. It is totally media independent. IP is unreliable. It cannot manage or fix undelivered or corrupt packets. It cannot retransmit after an error. It cannot realign out of sequence packets. And it has to rely on other protocols for these functions. Voice over IP is a perfect example in that with voice over IP, it is necessary for the packets to arrive in order. You cannot take a packet that has arrived out of order and put a segment of a voice call in where it does not belong. Because of the speed necessary for voice, we want to reduce the overhead. So user datagram or UDP protocol is used. But UDP does not use sequence numbers so that we would not know if a packet arrived out of order. We do not want to go to TCP, which would do that because of the overhead. So we combine UDP with RTP, Reliable Transport Protocol, to number the packets so that if something does arrive out of order in voice over IP, the packet would be dropped. IP is totally media independent. it does not concern itself with the type of frame required at the data link layer or the media type at the physical layer. Just like the truck from the post office, we do not know or care what model or make the truck is. The network layer does not know or care what type of connection is being made from the source to the destination. IP can therefore use any media type, whether it be copper, fiber, or wireless. The network layer will establish the maximum transmission unit, or MTU. Network layer receives this from control information sent by the data link layer. As discussed in a previous chapter, the size of an Ethernet frame is critical so that it is not too short, being a runt, or too large, being a giant. We would then set the MTU to work with the different type of media that we are using. As an example, when we use point-to-point protocol over Ethernet, this is normally the technology used for the telephone system when we get a DSL connection. Because of the additional information in the header for point-to-point protocol, the maximum transmission unit, or the amount of data each packet can carry, has to be reduced. Fragmentation is when the layer 3 splits the IPv4 packet into smaller units. Now, instead of having one unit for transmission, we have 2 units, increasing the amount of overhead and therefore causing latency. IPv6 does not fragment packets. Here, as an example, a router goes from Ethernet to a slow WAN with a smaller MTU. In this case, the router would have to fragment the packets to accommodate the smaller MTU. The IPv4 packet header is the primary communications protocol for the network layer. This is gradually changing until IPv6 becomes the main protocol used worldwide. The network header has many purposes. It ensures the packet is sent to the correct direction, or in the correct direction, so that it reaches its destination. It contains information for network layer processing in various fields. The information in the header is used by all layer 3 devices that handle the packet. As we can see here, first, all the information in the header is in binary. It contains several fields. The diagram to the right is read from left to right and top to bottom. As we can see here, the first field is the version. This would tell us whether we are carrying IPv4 or IPv6. Then we have the internet header length, so that we know how long is the header and where should the data begin. The next field is for quality of service. So these bits would be set to indicate what type of traffic we're setting and what quality of service do we need to give it. The next field would tell us our total length. Then identification, any flags that we may need. If we have fragmented, what is the offset for the fragment? The next field is a very important field, the time to live. If the packet cannot get to its destination, we do not want it going endlessly through the network. This would be a huge waste of our bandwidth. So in the time to live field, we would have a number, and each router that it goes through would reduce the number by 1. When that number, the time to live number, reaches 0, the packet is just dropped. It is considered to be unreachable as far as the destination is concerned, so we drop it. The next field tells us what layer 4 protocol we are carrying, so layer 4 would then be able to process the data correctly. We have a header checksum to make sure that the header has not been corrupted in transmission. And then we have the source and destination IP addresses. You may notice on the right, the entire length of the header for IPv4 is 20 bytes. Some of the fields that we have discussed, the version before IPv4 as opposed to IPv6. An IPv4 would have 0100 or 4 in binary. The differentiated services or diffserv. This provides us quality of service. Other types for quality of service besides diffserv is interserv and type of service. We also have a header checksum, and this would detect corruption in the header. The time to live, as discussed, is a countdown timer for each router that it goes through. When it becomes 0, the packet is discarded. The protocol fields tells us what IP or what layer 4 protocol is being used. And then the source and destination IPv4 addresses. An IPv6 packet as opposed to an IPv4 packet. IPv4, we had severe limitations because when it was originally developed, the explosion in the use of the internet was not considered. So IPv4 address depletion. We ran out of IPv4 addresses. Because one of the processes that was created because of this depletion was network address translation, we ended up with a lack of end-to-end connectivity in that the same IP address does not continue throughout. So to make IPv4 survive this long, private addressing, these are addresses that anyone can use but are non-routable over the internet. Most of you are using private addressing. Private addressing will be discussed later in Chapter 11. Since private addressing is not allowed over the internet, and most of you are using private addressing, you may wonder why you're able to get out to the internet. This is because network address translation was created. And because of that, it ended any kind of direct communications with the public addressing. It also has increased network complexity. NAT was meant only as a temporary solution and creates issues on the network. The side effect of manipulating the network headers and addressing, NAT causes both latency and troubleshooting issues. At this point in time, we also have NAT that is used for IPv6 for the occasion when we are going through either an IPv4 network with IPv6 information, or we are going through an IPv6 network with IPv4 information. In either case, we must use NAT to change it over to a protocol that allows it to be transported from one destination to the other. IPv6 was developed by the Engineering Task Force, the IETF. It overcomes the limitations of IPv4. As we can see in the chart, IPv4 had approximately 1 billion addresses. IPv6 has 1 undecillion addresses, a huge increase in addresses. So the improvements, we have an increased address space based on 128-bit addresses, not 32 bits. If you recall from the chapter in number systems, each time we add an additional bit in the binary number system, we double the number of addresses. So 33 bits would double the number of IPv4 addresses currently available. 34 bits would multiply it by 4 times. If we keep going out to 128 bits, it becomes a huge address space. It has been said that there are enough addresses in IPv6 to address every grain of sand on the planet. I do not know whether that is a correct assumption, because the last time I was at the beach, there seemed to be a lot of sand. I do know that it would provide enough information or enough addresses for every man, woman, and child on the planet, along with the entire Internet of Things, and we would not even touch the amount of addresses that we have. It also has improved packet handling. We have simplified the header with fewer fields. And it eliminates the need for NAT. Since there is a huge amount of addressing, there is no need to use private addressing, either internally or to be mapped to a shared public address. But as mentioned earlier, right now, because we are using both IPv4 and IPv6 in a transition period, we do have network address translation for IPv4 and IPv6. The IPv6 header, as you can see, is much simplified compared to the IPv4 header. You may notice that the header is fixed at 40 bytes or octets long. This is longer than the IPv4 header, mainly because of the length of the IP addresses. Several of the IPv4 fields were removed to improve performance, and some of the ones that were removed were the flag, the fragment offset, and the header checksum. You may notice here a field called hop limit. The hop limit is equivalent to the time to live field in IPv4. Version for IPv6 in binary would be 0110 or 6. The traffic class is for our quality of service markings. So version for IPv6 as opposed to IPv4, the 4-bit field will be 6 in binary or 0110. The traffic class is for quality of service. The flow label informs a device to handle identical flow labels the same way. The payload length, and this is a 16-bit field, indicates the length of the data portion or payload of the IPv6 packet. The next header, this gives us IDs, the next level protocol, such as the information for layer 4, whether the protocol that we are transporting be ICMP, TCP, UDP, or any other particular protocol that would be distinguished at layer 4. The hop limit, again, replaces the layer 3 time to live field in IPv4. Here you may notice an error. It is not the source IPv4 address or destination IPv4 address. It is the source IPv6 address and destination IPv6 address. An IPv6 packet may also contain extension headers. We normally do not fragment IPv6, but if it becomes necessary, we have an extension header which would give us additional information. They provide optional network layer information. They are totally optional. They are placed between the IPv6 header and the payload and may be used for fragmentation, security, mobility, support, or others. A host must make a decision of how to get to the destination. So packets are created at the source, being an end device. Most common for this class would be PC. It can also be a phone. It could be a voice over IP phone. It could be many other types of device, not necessarily a PC. Each PC, though, will generate its own routing table. A host can send packets to the following. If we want to test whether the protocol stack and our network interface card is working, we could use a command ping to 127.0.0.1. This is a loopback address that we can use to test our own interface. For IPv6, it would simply be : 1. We could also send packets to local hosts where the destination is on the same LAN. If it is on the same LAN, we technically do not need an IP address, as it would be regulated by the data link layer at layer 2. If I need to go to a remote host, I must have some type of IP addressing. To make a forwarding decision, the source device determines whether the destination is either local or on a remote network. IPv4 source will use its own IP address and subnet mask along with the destination IP address to determine if the destination is on the same network. For IPv6, the source uses the network address and prefix advertised by the local router. Local traffic is dumped out the host interface to be handled by an intermediary device, such as, in this case, the switch. Remote traffic is forwarded directly to the default gateway on the LAN. In this case, our default gateway is the router R1. The default gateway just means this is the way to get out of your current network into other networks, such as in a building that only has one door. If you want to get out into the outside or another building, you must go out that door. So any kind of traffic that is destined for another system must take the default gateway at the router being the exit door to other networks. A router or layer 3 switch can also be a default gateway. A layer 3 switch does routing as well as switching. Your home router, even though it's called a router, is a layer 3 switch in that you have multiple ports, which are the switch portion, and it sends it out via the routing portion. Features of a default gateway: it must have an IP address in the same range as the rest of the LAN. It can accept data from the LAN and is capable of forwarding traffic off of the LAN, and it can route to other networks. If a device has no default gateway or a bad default gateway, its traffic will not be able to leave the LAN. The host will know the default gateway either statically or through an address that it has received via DHCP, Dynamic Host Configuration Protocol. IPv6 sends the default gateway through a router solicitation or RS message, or can be configured manually. Many times configuring either IPv4 or IPv6 manually, the default gateway could be configured incorrectly. The default gateway is static route, which will be a last resort route in the routing table. If I have a route that matches the network that I need to go to, that would be used before a static route going to a default. All devices on the LAN will need the default gateway of the router if they intend to send traffic remotely. Your PC maintains a routing table from places that it has gone. Entries in the routing table will also time out and be removed. If you want to see the routing table on your PC, you can select in the command prompt, route print, or netstat space -r to display the routing table. 3 sections displayed by these 2 commands: the interface list, so all potential interfaces and MAC addresses, the IPv4 routing table, or the IPv6 routing table. I once had to repair a computer that had a virus that, for anything to go out to get antivirus, it would loop back to the 127.0.0.1. So the computer could never get out to any of the antivirus companies to get the antivirus to remove the virus, as it was stored in this routing table to loop the user back to themselves. The routing table had to be edited in order to go out to get the antivirus. When we talk about having multiple networks, we must be able to route information. You may recall that routing protocols versus routed protocols are much different. A routed protocol contains enough information, such as IPv4 or IPv6, so it can be routed from network to network. A routing protocol is what routers use to exchange information about the networks that they are either directly connected to or that they have learned about. In this case, a packet going from PC1 to PC2. So the packet arrives at the gigabit Ethernet 000 interface of router R1. Remember that at that point, it is technically a frame. The router will strip off the layer 2 information to get to the packet. So router 1 de-encapsulates layer 2 in Ethernet header and trailer. Router 1 would then examine the destination IPv4 address of the packet and search through its routing table for the best match. The most accurate match is the one that is used. Once that has been determined, the route entry indicates that this packet is to be forwarded out to router R2. Router 1 re-encapsulates the packet into a new Ethernet with a new Ethernet header and trailer, creating a new frame, and forwards the packet to the next hop router, which is R2. R2 would, just like R1, strip off the layer 2 information, examine the network that the packet needs to go to. In this case, it is directly connected. It would re-encapsulate the packet, creating a frame for distribution out onto the Ethernet network, as we have seen here, connecting to PC2. The routing table can have different types of route. First, directly connected. And these are automatically added by the router. These are the interfaces that are directly connected to the router. As a point of information here, when we configure a routing protocol, we only configure the routing protocol with the networks that we are directly connected to, no others. We learn about the other networks through the routing protocols. There are remote routes, and these are routes that we have learned through a number of methods. So these are routes the router does not have a direct connection to and may be learned either manually, we could put in a static route, or dynamically by using a routing protocol. We may also have a default route. This forwards all traffic to a specific direction when there is not a match in the routing table. Your home router would use a default route that any network that it does not directly know of would be sent out to your ISP. In the case of our diagram here, it would be very easy to say we could use a routing protocol between R1 and R2, or that could also be configured with static routes. For a simple network, sometimes static routes are the better choice because they do not use the amount of processing power that a dynamic routing protocol may use. In either case, as in our diagram, router 2 would more than likely use a static default route to get out to the internet. There was a case in Pakistan where a static route was placed by order of the government to the tier 2 ISP. government did not want residents of Pakistan to be able to go out to YouTube. The service provider, providing all services for Pakistan, put a default route so that anything that was meant to go to YouTube would be sent to a null zero interface. A null zero interface could be thought of as a large waste paper basket where things could be dumped. The problem occurred when the static route that was entered for YouTube, which would have a perfect metric, no cost because it was entered statically, was distributed from the Tier 2 provider to the Tier 1 provider in Hong Kong. Normally, this would never be the case because it would normally go from the Tier 1 providers to the Tier 2 providers, never in the opposite direction. Within minutes, the Tier 1 provider in Hong Kong exchanged that route for YouTube to every other Tier 1 provider within the world. And within minutes, no one in the world could get to YouTube because anything trying to get to YouTube was routed to the null zero interface in Pakistan. This just demonstrates how fragile the internet could actually be if routing isn't taken care of in a very precise manner. Static routing is done by entering the command as shown on the right, IP route, the network and subnet mask that we are trying to go to, and either the next hop or the exit interface. They are configured manually. They must be adjusted manually by the administrator if there is a change in topology because they will not automatically change. They are very good if we want traffic to go in one particular direction. But as seen in the lower part of the diagram, if the connection between R1 and R2 failed, a static route would not be able to adjust for that. And so the destination would become unreachable. We can add in additional static routes to compensate for a link going down. But the more routers that we have and the more networks, the number of entries would become very large. So static routes, they are good for small, non-redundant networks. In such as the case in the upper diagram, R1 has only one way to go out to get to the internet. It must send all information to R2. And it is often used in conjunction with dynamic routing protocols for configuring a default route. A default route is normally referred to as a quad zero, whereas instead of having the route such as the 10.1.1.0 and the subnet mask, a default route would be 0.0.0.0 with a subnet mask of 0.0.0.0. This says anything that you do not know about, send it out this way. If we do not have a default route and the network that we are looking to go to is not in the routing table, we would not be able to transmit information to that network. Dynamic routing will discover remote networks. Each router will exchange information about the network that it is connected to. or has learned of. It maintains up-to-date routing information. It will also choose the best path to the destination. Some routing protocols do this better than others. Routing Information Protocol, or RIP, is only concerned with the number of routers that it must go through to get to the destination. It does not concern itself with the speed of the links. So it may take a slower link in preference to a faster link simply because it has one less router to go through. Other protocols, such as EI-GRIP, will take into account the speed of the link, the load at any particular time, any kind of delay, and many other metrics to make it a much more efficient system. But because of the additional metrics, it is also a harder protocol to configure. The dynamic routing protocol will find the new best path when there is a topology change. We must make sure that other routers do not attempt to change the information once a network goes down. We therefore use 3 different methods to make sure that when a router is updated, the information is accurate. One is split horizon, in that we never send information back out in the same direction that we received it from. The other is a hold down timer, so that we wait and we will not accept information until the timer has expired. The third is that we will poison the route, in that we will make the metric or hop count so great that the route will not be used for a certain period of time. Routers can also share their static default routes with other routers. As in the case of Pakistan, they shared their static route with the rest of the world. In a routing table, as shown in this diagram, you have entries that are labeled L. At the top, you normally have the codes used in the routing table. L is directly connected local interface. As you may see in the diagram, 192.168.10.1 is the actual address of gigabit 000. It is not the network. The network is directly above that, 192.168.10.0 with a /24. So C is the directly connected network. L is actually the local interface. S is a static route, and here you see the example of a quad 0. And this becomes the gateway of last resort. So if we do not have an entry in the routing table, the static route would be used to get the information to the destination. An entry with a O stands for OSPF, or Open Shortest Path First, which means we learned about the 10.1.1.0 network via 209.165.200.226, or Ethernet 001. And that's how I would get out to that network. You may notice in the brackets 110/2. The 2 is a metric of the cost to get there. The 110 is what we refer to as an administrative distance. Each routing protocol has an administrative distance associated with it. The higher the administrative distance, the less trustworthy that route or routing protocol is. RIP, as discussed earlier, has an administrative distance of 120. OSPF has an administrative distance of 110. EIGRIP, which would be designated by a D, has an administrative distance of 90. So if the router had networks with entries coming from RIP, OSPF, and EIGRIP, all for the same network, the only one that would appear in the routing table would be the EIGRIP because the administrative distance is lower, therefore more trustworthy. The star next to a static route indicates that this is a candidate for being a default route. To demonstrate static, dynamic, and default routing, I have opened Packet Tracer. Packet Tracer is a free download if you are a member of the Cisco Academy. It is a very useful tool for simulating networks. It does not replace real equipment, but it is very close to using real equipment. I'm going to bring in two routers. We look down at the bottom. The first is network devices, and then I have a selection of routers that I can bring in. I'm going to bring in two of the 4331s. These are the same routers that we use in the lab. Now, I need to enter a serial port on these two routers. This is a physical piece and must be done at the router interface. I have brought up the router. As you can see, we have the physical connection, we have configuration, we have command line, and we have attributes. First, I'm going to go to the physical connection. In Packet Tracer, if I try to add the serial connector in, it's going to tell me I cannot while the power is on. First, I will shut the power off, add in the physical connector, and then put the power back on. You can make sure that the power is back on by going to the command line, and you'll see the operating system is now decompressing. After it decompresses, the router will ask me if I would like to enter the initial configuration dialog. Normally, we would choose no. For this example, I'm going to choose yes to show you how to escape from that mode. If I say yes, it's going to go through and ask me a series of questions, many of which you may not be using in the lab. To get out of this mode, you hit Control C, and it will return you. Notice that we are in router with a greater than sign. This is user mode. It allows us to do very little. If I want to get into privileged mode, I will type in enable, and hit enter. I did not necessarily have to type in the entire word enable. I only have to type in enough of the command to make it unique. For enable, since it is the only word that begins with en as far as a command is concerned, I could just type in en and hit enter, and it would still enable. I want to change the name of this router. So first I have to go into configuration terminal. I could also, instead of configuration, it just needs to be configure. At any time, if you are not sure of a command, you can use the question mark. Here, you'll notice after I've typed in configure terminal, which I could have abbreviated with config space T, it puts me into global configuration mode. Global configuration mode is used for things that are globally significant to the router. In our case, the name is globally significant. So I'm going to change the host name to R1. For proper names, we normally use capital letters. That makes it much easier to figure out what is a name versus what is a command. Notice that the router's name has now changed to R1. If I want to see what interfaces are available on that router, I can also type in our case, because I am not in user mode, I am in a configure mode, global configuration, I have to say do first, which tells it to look through the other menus to find the command. And I'm going to say do show IP interface brief. And it will show me the commands or the interfaces that I have. You'll notice we have a gigabit 000, 001, 002. We also have the two serial ports that I just installed, serial 010 and serial 011. I have brought up the second router because here too I must have a serial port to connect the two routers together. So first I will shut off the power, place the serial port in the slot, turn the power back on. The two slots are the same so that you could enter the serial port in either one. The naming convention would change depending upon which slot the serial port has been put in. I will switch to the command line view, and it is asking me if I would like to enter the initial configuration dialog. To this, I will say no. You'll notice because we have not configured, the name is router. We'll type in enable. I can also type in just en and hit the tab key, which will complete the command. I then must go to configure. And if I have a command that is made up of multiple words, I can type in the first, hit tab. Notice I had to put in the F because there are multiple words that begin with CON. If I want to see the options that begin with CON, I can go back and put a question mark directly after the CON. So I have two commands that begin with CON, configure and connect. So to make this unique, all I would need is CONF. Now I can type in the tab key and it will complete the word configure. If I want to see what options are available to me there, I can type in the question mark and it will show me. Here I only have one, configure terminal. So I can type in AT and that would be enough. If I want the entire command, I can put the T and then the tab key. Notice again, we are now in global configuration. I will now change the host name to R2. As in the other router, which I named R1, I do not want them to be named the same. Now that I have named the two routers, you'll notice on the main page of Packet Tracer, the names here have not changed. Changing the names in the configuration does not change the name that is displayed. I can click on the name that is displayed and I will name it the same as what I named in the configuration mode. Since I have installed the serial connectors on either router, I can now connect the two routers using a serial link. I'll go to the lightning bolt, which is my connections. The red lightning bolt with the clock is a serial connector. The clock indicates that the first connection I make will be the DCE, which normally gets the clock rate. You'll notice I can connect this to either serial 010 or 011. If I were to try to connect this to a gigabit port, it will tell me that that cable does not go with that particular port. I'm going to connect to 010 and I will connect on the other side to 010 also. I do not have to, but to just keep things simplified, I will. I'm now going to bring in some end equipment. If I go down to our menu, the second icon over is end devices. And I'm going to bring in a PC, and two servers. Now I'm going to connect these directly to the routers so that I will need a crossover cable. The crossover cable, if I went back to cables, crossover cable is the black dotted line. This is an Ethernet crossover cable. And I will connect from my fast Ethernet on the host computer to gigabit 000. I will connect from my server, fast Ethernet, to gigabit 000, and from the second server that I will eventually use as my ISP, I will connect from that fast Ethernet to gigabit 001. I'm going to rename these three devices. I will rename the host computer as PC-A. The first server which I will be using as my company's web server, I am just going to name this as www for World Wide Web. The second server I will rename as ISP to indicate that that is my connection to the outside world. I'm now going to modify my two servers. I have clicked on the server and has brought up the diagram of my server. You'll notice it shows me the physical, configuration, services, desktop, programming, and attributes. I'm going to go to services. You'll notice that I have this index, which I can edit. This is the main screen that comes up when we will access the server. Right now, it says Cisco Packet Tracer. I'm going to change this to Module 8, www server. I will then tell it to save this. It's going to ask me if I want to overwrite, and I will say yes, because I do want to save this. I have brought up the second server, where again I will go to Services, enter to edit the index, and change where it says Cisco Packet Tracer to Module 8, ISP server. I will then tell it to save that, and again it will ask me if I want to overwrite, which I will say yes, and I will save the file. I've now returned to the main screen. I need to configure addressing. So first, I want to configure what addresses I will use. I'm going to use the note function to place the addresses, just to remind me of what address range will be in each location. The serial link will have 10.0.0.0 with a /30 mask. The link going to PCA will have the 10.1.0.0 with the /24 mask. The link going to the company's World Wide Web server will have 10.2.0.0 with a /24 mask. And my simulated ISP will have the 200.0.0.0/24 mask. I can move these around to make it look much neater. Now that I have determined the addresses that will be appropriate for my network, I can configure each of the devices. I have gone into R1, and you'll notice that after I have named it, Up at the top, it now says R1. It has put me back into user mode because of lack of activity. So I need to get into privilege mode where the command is enable, or all I need to put in is the EN. Notice that my prompt has changed to the pound sign. I now want to get into global configuration mode. So I can just type in config T. I now need to start configuring my interfaces. The first interface that I will configure is the serial port. So I will say interface serial 0/1/0, the link that I connected the serial cable to. It is always a good idea to put in a description of where does a particular connection go. So I will say description, connection to R2. I can now enter the IP address. You may have recalled that I gave this network the 10.0.0.0 network with a /30. The first address would be 10.0.0.1, and a /30 when written out as the subnet mask is 255.255.255.252. Because this was the first connection that I made, it also needs to receive the clock rate. Normally, I use 2 million as my clock rate. Clock rate is 2 words, so I had to go back. Notice that I get the caret indicating that I have typed in something wrong. If you receive the caret, it means that it did not take the command, and you need to go back and edit the command so that it is acceptable to the operating system. I have now given that interface an IP address and a clock rate and a description. The only thing that I have left to do is tell it to turn on. So I will put in the command no shut. This tells the interface to turn on. You'll notice that we got a message that it changed state to down. This is normal because we have not configured the other side of the connection. I now want to configure the connection that goes to PCA. So I can say interface gigabit 0/0/0. Notice I did not have to spell out gigabit. I just had to put in a G indicating that it was the gigabit connection. You'll notice here the prompt does not change between the serial interface and the gigabit interface. It still says config-if for interface. I will now put in the description. And I'll just name it as description connection to PCA. I'll now enter the IP address. And For this network, we were using the 10.1. Now I am going to give it the 10.1 address that is the very last available, which would be 10.1.0.254. The subnet mask, because it was a /24, will be 255.255.255.0. Now, an Ethernet connection does not get a clock rate as does the serial, and only one side of the serial gets the clock, the DCE. One way to remember it is C for clock. Here, I put in all the information to get it working. There are many more commands that we could put in to influence the connection, but at this point, we just want to get it up and running. So we say no shut. Notice that here it said change to up, and that is because the PC is connected and will automatically bring it up. The PC's network interface card is always on, whereas on the serial connector, the connecting point at R2 has not been turned on because we have not given it the no shut command. I have selected PCA, and you'll notice that I have physical, configuration, desktop, programming, and attributes. I'm going to go to the desktop, which will allow me to change the IP address. I will select IP configuration, and I have the option of either letting it get an address dynamically through DHCP or statically. I'm going to enter a static address. This is the 10.1 network. I used the last host address, the 254, for the router. I'm going to use the first for the host computer, PCA. The subnet mask must be the same in both, which was 255.255.255.0. The default gateway needs to be the same as the interface on the router, 10.1.0.254. It is good practice that after configuring both ends of a link to test the link to make sure it works. I'm going to use the command prompt, and I'm going to ping the router. So I will say ping 10.1.0.254, the address that I entered on the interface of the router. You'll see that I've gotten a reply. This tells me that that connection is good. I've now moved to router 2, which I can see in the upper left tells me I am in router 2. Again, due to lack of use, it has put me back into user mode. So I will type in EN for enable to put me into privilege mode, and then config T puts me into global configuration mode. I can now program my interfaces. First, I will program interface serial 0/0/0/1/0. description, connection to R1. I will now enter the IP address. I used 1 for router 1. This will be 2. The subnet mask must be the same on either side of the link. A /30 is a 255.255.255.252. This side is the DTE connection, data terminal equipment, as opposed to the other side that I connected the DCE connection, data communications equipment. The DTE side does not get the clock rate as the DCE side did. So all that is necessary here is for me to enter the command no shut. And we will see that it will tell me it has changed its state to up. I can now proceed with my configuration of my gigabit ports. So I will say interface gigabit 0/0/0. You notice that I do not have to go back to global configuration. I can move from one interface mode directly to another interface simply by typing in the command. Description, connection to www server, IP address, and this was the 10.2 network, 10.2.0.254 being the last usable host address in that network. It has a subnet mask of 255.255.255.0. I can now turn it on with the no shut command. And we'll see that it changed state to up because the network card on the server is already up. It does not have an address, but that does not stop it from being electrically up. I'll now configure interface gigabit 0/0/1, the connection that goes to my ISP server. So I will say it has a description, connection to ISP server. IP address 200.0.0.254. And because I specified this to be a /24, the subnet mask would be 255.255.255.0. If you recall, in a dotted decimal IP address for IPv4, each grouping is an octet, 8 bits. So if I have 8 ones in the first octet, 8 ones in the second octet, and 8 ones in the third octet, it adds up to 24. And that is where the original /24 came from. I can now turn on this interface. No shut. Now, because the serial connection is now up, I need to check that to make sure that it is working. So, because the ping command isn't in the configure IF menu, I can tell it to look for the ping command by saying do first. Ping 10.0.0.1, the address that we put on the interface of R1's serial port. You'll notice that I have gotten a successful reply from R1. I have brought up the World Wide Web server, as we can see by the www, and I want to enter the IP address on this. So I went to the desktop and chose IP configuration. This will be the 10.2.0.1. And the default gateway will be the router, which we gave the address of 10.2.0.254. Once that information is entered, I can use the command prompt to check my connection. And you'll notice that we have gotten a reply. I have moved to the ISP server. Again, I will go to the desktop, click IP configuration, and give it a configuration IP address. For the ISP, we are using the network 200.0.0, and the first address will be 1. I gave the last address of 254 to the router. The subnet mask is 255.255.255.0. And the default gateway will be 200.0.0.254, the address that we assign to the router interface. To test this link, again, we will go to the command prompt and ping 200.0.0.254. And I have gotten a successful reply. Moving back to the main screen, we can now see that all of our links are up, indicated by the green triangles. We have also tested through the ping commands each one of our links. As you are building a multi-link network, it is good practice that after configuring both ends of a link, to check it using the ping command. It is not good practice to build everything and then find out that certain things are not working. Because if you have overlapping addresses, you need to go back and configure a great deal more. We will now see if we can get through our network. I have moved back to PCA. First, I want to see if I can ping my World Wide Web server or the ISP server. So I will say ping 10.2.0.1. This is the address that was assigned to the World Wide Web server. You'll notice that it tells me the destination is unreachable. This is because the routers do not know where the network is. I have moved to R1. Again, due to lack of activity, it has taken me out of privileged mode. So I need to get back in. Enable. Then I want global configuration. Config T. Now I am going to enter a static route. And this is actually going to be a default static route. Because the only way that R1 can get to the rest of the world is out through the serial connection, I can say anything that it doesn't know about, send it out that serial port. Or I can say send it to the next address, the address of R2, which is what I will do. The command is IP route, and then to make it accept any address, any unknown, we will say 0.0.0.0, 0.0.0.0. And then we have to say anything that you don't know about, send it to 10.0.0.2. You may recall this was the address of R2. I am now going to enter what's referred to as an administrative distance. Routing protocols have an administrative distance. The administrative distance indicates the reliability of the protocol. A protocol that takes in more metrics is more reliable than one that takes in fewer. Routing Information Protocol, or RIP, has an administrative distance of 120. This is because RIP is only concerned with the number of routers or hops that it goes through. It is not concerned with the speed of the link. So it would choose a slower link that had one hop rather than a faster link that had two hops. Other routing protocols use other metrics and as such would have a lower administrative distance. When I enter a static route, it would give it a perfect administrative distance of 0, which would override everything else. The problem with a static route is that it would be used over a dynamic route because of the lower administrative distance, even if a network connection went down. It cannot adapt to changes. I'm giving this the 200 so that when we put in a dynamic protocol, this route will no longer be used and we will see the change to the dynamic protocols. So this is saying anything that you don't know about, send it to the next router. I am now on the next router, R2, which just timed out, so I have to type in enable and config T. This now needs to know how to get to the 10.1 network. In routing, you not only need a way to get to your destination, but the destination needs to know how to get back to you. So we will say IP route for the 10.1.0.0 network, 255.255.255.0, send it to 10.0.0.1, the IP address of R1. And again, I will give this an administrative distance of 200. Once those have been entered, the routers now know how to transfer the data. Because the ISP is directly connected, we would be able to get there. But if it was an address somewhere else in the World Wide Web, it would not know how. So we need to put in a default route for this router saying that anything that you don't know about, send it to the outside world, send it to the ISP. So we'll say IP route 0.0.0.0.0, 0.0.0.0, and we're going to say send this out gigabit 0/0/1 rather than an IP address. In your home, you may not know what is the IP address of your ISP. So your router would send it out the connection rather than to a specific address. This is going to give us a warning message because since it is Ethernet, it assumes that there could be more than one connection at the other end. For our purposes, it's not going to affect us. And you can see here we did get the warning message that a default route without a gateway, if not a point-to-point interface, may impact performance. That is acceptable for what we are doing today. Returning to our main screen, we should now be able to select PCA and ping both to our World Wide Web server and our ISP server now that we have entered the static routing. Selecting PCA and going to the command prompt, can now see that if I ping 10.2.0.1, our World Wide Web server, I do have a connection. I could also ping the 200.0.0.1, the ISP server, to verify a connection there as well. I can also use the web browser to go to either server, the 10.2.0.1, and you'll notice it does say Module 8 www server that we programmed in earlier. If I went to the 200.0.0.1, we'll see that it is the Module 8 ISP server that we programmed in earlier as well. I have moved back to R1, and I also extended the width of the design. This is so that we will be able to see the printout in a much easier fashion. I am in user mode, so I need to change to privilege mode, enable, and I need to change the global configuration. First, I want to see what my routing table looks like. So I'm going to say do show IP route. And you'll notice that right now I have directly connected to C, and that gives me the network. L's give me the local interface. Notice the 1. Here is the static route that I entered earlier. Notice the 200 for administrative distance. The star indicates that this is a candidate as a default route, and we see that up here as the gateway of last resort. I'm now going to enter a routing protocol. I am going to use OSPF, or Open Shortest Path First, because this is an open standard. It's probably the most popular protocol used in the world today. The way that we enter this is we say router OSPF 1. The 1 is a process ID. It is not necessary that all routers in the network have the same process ID in OSPF. Some businesses may use one process ID to indicate the engineering department, possibly worldwide, while they may use a different process ID for other departments. For our use here, we will keep the process ID the same on both routers. After I have entered my router OSPF1, you'll notice how my prompt changed to configure router. I now must give OSPF an ID. So I will say router ID. And the ID is always in an IPv4 format. Because this is router 1, I'm going to give it 0.0.0.1. I now must enter the networks that I am directly connected to. You only enter directly connected networks, not every network that is in your design, only directly connected. And the way we enter this is with a network command. And my PCA network was the 10.1.0.0, and then I must put in a wildcard mask. The wildcard mask is the inverse of your subnet mask. So in our case, the subnet mask was 255.255.255.0. The wildcard mask will be the opposite of that, or 0.0.0.255. OSPF uses areas. You always have to have area 0, which is your backbone. Areas are covered in a later course. Here, we will just say it is area 0. And that's all I need. There are many more commands that we can do in OSPF. It is a very robust protocol. But here, just beginning, we will keep it as simple as possible. I have one other network, the serial link that connects between router 1 and router 2. So we will say network 10.0.0.0. The subnet mask was 255.255.255.252. So the wildcard mask will be 0.0.0.3. If you add the wildcard mask along to the subnet mask, you will end up with 255.255.255.255. This will also be part of area 0. That's all I need do at this point. If I want to show my routing table again, I can say show IP route. I have to put do in front of that. The routing table hasn't changed. Why? Because we have not configured R2. I have switched to R2. Again, in the upper left, it shows us the name. I have to get back into global configuration mode. So first I have to get into privilege mode by enable, or just EN. Config, terminal. I can now put in my OSPF commands. So I will say, but first, before I do that, I will say do show IP route. And you'll notice this is what we have at this point. I have the static route with the star indicating that it is a candidate to be a default. And if we look above at the gateway of last resort, there is my default route to go out. Currently, I only have directly connected, link locals, and static. I'll now put in my routing protocol, router OSPF, and I will use the same process ID of 1, but it must have a different router ID. Since this is router 2, I will say that the router ID is 0.0.0.2. I will now put in my networks. Router 2 has 3 networks attached, and they are network 10.2.0.0, 0.0.0.255. Area 0. Notice how it told me it was an incomplete command because I had neglected to put area 0 at the end. You can get the caret if you have mistyped something, or if you have not finished the command, it will show you incomplete command. I will not be putting in the network going to the ISP. You never exchange routes with the ISP. You use a default route, as we put in earlier, to go out to the ISP. So that will not be part of our network commands. The next network command is for the serial link connecting R1 to R2. When that has been put in, we will see that we will get an adjacency between the two routers. Network 10.0.0.0, 0.0.0.3, area 0. Notice that we just got an adjacency with a router with a ID of 0001 coming in on our serial 010 interface, and we went from loading to full and done. That means we are now exchanging routes. If I go back and now say do show IP route to see my routing table, we will see another entry. And it begins with an O, indicating that we received that network via OSPF. So now the router knows how to get to the 10.1 network. Earlier, if I scroll up, we were able to get to the 10.1 area because I had put in that static route with an administrative distance of 200. Because OSPF has an administrative distance of 110, the OSPF route removed the static route because the administrative distance was lower. And as you can see here, the 110. The 65 is a metric that OSPF uses as far as the cost to get to a destination. If I had two possible ways to get to a destination, the one with the lowest cost would be used. The cost is determined by the speed of the links. Now, I also need to tell this router to exchange that default route going out that I put in. So the way that we do that in OSPF is we say default dash information originate. There are additional commands which will be discussed later, but for our use here, all we need is default information originate. This only goes on the one router where we have default information to go out to the outside world. If again we took a look at the routing table, there is no change. We will see a change in R1 though. Moving back to R1, and again shown by upper left corner, you always want to check that to make sure you're in the piece of equipment that you want to be configuring. You'll notice that we also got the message here that we got a neighbor when I put in the network command on R2. If we take a look, this is what our routing table looked like previously. We had the static route that I had entered with the 200 administrative distance. If I now say do show IP route, we'll now see that that route has been removed and this OSPF route has been inserted in its place. O for OSPF, the star indicating that is a default contender. E2 indicates that we got it through an external type 2 process. It was not totally OSPF because OSPF was redistributing a route that I put in statically. That's why it is an external type. Notice that it is 110 for OSPF, 1 because it is a perfect route. The only thing that would be more perfect is something that is directly connected, that is normally a 0 as far as a cost. So because the metrics of this route are better, this is the one that would be in the routing table. I could also say do show protocols. And it will tell me that my internet protocol routing is enabled. My gigabit lines are up. I could also say do show IP protocols. And this will tell me more about my OSPF. My process is OSPF1. I don't have any filters. These are the networks that I am routing. Here are the routers in my network, the 1 and the 2, the IDs. The administrative distance, 110, which is the default for OSPF. And when was the last time I got information from them? As I said earlier, OSPF is a very robust protocol, so it can do many different things. We can configure it very simply, or we can get more and more complex. I've moved back to my World Wide Web server. prove that we can get to the ISP. So I was able to get to my ISP server. I can also prove that I could get to my PCA. So I could say ping 10.1.0.1. Moving back to my main screen, we've now proven that I have full connectivity throughout my network. We have made this network work both with static and default routes, along with a dynamic routing protocol. Some simple networks, static routing works very efficiently. It does not use any processing power. We use this many times in what we refer to as a stub network, a network that only has one way out. There is no need, in that case, to use a dynamic protocol which takes up your bandwidth and processing power. If there's only one way, that's the road that must be taken. A good network design will include static, default, and dynamic routing. Could you do a large network with only static? Yes, but the number of entries that would have to be made would be extremely complex for the number of routers. One advantage that static does have in a large network is that you can always control the direction that information will flow. But as I said earlier, the more routers that you have, the more complex it is, because static does not adapt. There are ways to enter multiple static commands, which we refer to as floating static, so that it can adapt, but it becomes a very complex situation. After we are done, we could save our diagram using File and Save, or if it's not necessary, we can just exit out of Packet Tracer. This will conclude the video on Chapter 8.